Alrighty, how's everybody doing? Can you hear me? Last stream, I watched some, and it seemed like my mic was way too quiet to hear, like for my phone, on the highest setting. So is this too loud? Did I overcorrect? Let me know in the chat. Nobody told me. Nobody told me. Maybe I'm just too picky. I figure if nobody told me, it couldn't have been that bad. But it was bad for me, man. I was disappointed. Felt like I was doing a poor job as a streamer. But yeah, let me know how the audio is. I can adjust it as needed, but obviously that's important to take care of before we get started. How's everybody's day been? I'm streaming on Wednesday because I'm not allowed to be on schedule anymore. No, I mean, I'll try to keep up with it, but life's been crazy, man. I haven't been feeling that good. And the math for these is not particularly easy either, and I have other stuff that I do, so. Anyway, yeah. So like I said, we'll be getting started here in a second. Hopefully everything checks out on the stream end. I did set up some widgets for the stream today. So we should have alerts for subscribers. I don't know if it'll work. I think it's most likely not going to work, actually. But, you know, if somebody wants to try and test that out, maybe see if it pops up or not. I don't know, like subscribe and unsubscribe, or, you know, you can always send money on Super Chat. But just see if it works, because I think it's supposed to work. I did all the tests in Streamlabs, and it, showed that it was working on the thing, but that doesn't mean it's going to work when we go live. My experience streaming is whatever you set up is just not going to work as soon as you press the go live button, no matter what, and then you have to figure out how to fix it as fast as possible. That's the actual streamer skill, is learning how to figure it out on the fly when there's a bunch of people watching, as opposed to trying to set it up and having it work on the first try. Doesn't tend to work out. Can you guys even hear me? There's no chat action, but there's only 8 of you here, so I'm not sure. Maybe it's just me. Yeah, it looks like the mic's on. We're good. Seven concurrent viewers. That's all right. Last stream we had picked up a lot more traction towards the end of the stream, so maybe it'll just be slow at the beginning here. Not sure. Maybe Wednesdays just aren't the day to stream. Yeah, we're going to be doing the first 11 problems from week 3 of the UChicago RU 2019 Math GRE Prep. I have dropped the link in the chat many times before for these problems, but if any of you are interested and you want to follow along with what we're doing, I can give you the link, but I will be flashing the problems on the screen as we go through them, so don't feel like you need to do that. But yeah, I think we'll just hang out and talk for a couple more minutes, or I'm talking to myself, I guess, because not much going on in the chat right now, but that's all right. That is all right. Got some good problems today. They're good. There is one topology one I'm not going to do, frankly, because I don't want to. But the other 10 I will be giving full solutions to. So yeah, should be good. There's one triple integral I haven't prepared fully, but I think it'll be fine. If anything, I'll make a bunch of simple arithmetic and calculus mistakes, and then we'll have to go back and catch it. But chat's usually pretty good at yelling at me when I make a simple mistake, so I'm not that worried about it. Oh, good. Yeah. Like I said, last stream, I don't know how big the stream delay is, but last stream, I feel like the audio was way too quiet from what I checked. But I think also when YouTube takes the stream and makes it a video, it compresses it or something weird, so it's possible it was fine live and not on the replay. But I can always make myself louder, and then obviously let me know if I'm too loud. But yeah, like I said, we have stream alerts. Maybe we have stream alerts. I don't know. Kind of waiting for one to go. But I should have them set up for new subscribers and super chats and stuff, but I don't know, like I said, all the test ones worked, but I don't know if it'll actually work if someone does it. I think we're good on that front. How's everybody's day going? Everybody doing good? How many of you are in school right now? I'm kind of curious. How many of you are like undergraduate, graduate students, and how many of you are like adults or PhD, graduates or professors, stuff like that? I'm curious. Because I feel like mainly this stream is useful for undergraduate and graduate seeking students that are like closer to me, but obviously it's for everybody. And I think that, just reviewing math, no matter where you are on your journey, is really beneficial, as I'm finding out through these problems. Because some of this stuff I haven't done in years. Years and years and years, even the easy stuff. Grade 11, wow. Yeah, no, I wish I had been on to checking resources like this, that early. Because when I was in 11th grade, I was taking Calc 1 and 2. And, I flew by the seat of my pants. So I kind of wish I had taken it a little more seriously. But also just, you are found resources that are available that would have made it way easier for me to get through the subject. Because I feel like I struggle a lot, mostly because it was just me and my textbook, and having someone else explain it or having another perspective is super beneficial, I think. And I've learned that the most through, this journey with the channel, because, I obviously took classes with Michael at school, and he always had these lecture components online that he would recommend to us to go along with his in-class lectures. And that kind of supplemental material was immensely beneficial for learning, because if I couldn't remember something he said in class, I just had a recording I could go back to and look at where he explained it very clearly, and then you can rewind 3 times and look at the formula and go over the same example 30 times and study it really well till you get it. And that kind of opportunity is like, I undervalued early on, for sure. Anyway, I feel like it's been long enough talking. I'm going to go ahead and start doing some problems, hopefully adequately. So yeah, let me go ahead and flash up the first problem we're going to be doing today. So let's see. There we go. Okay. So this is just an integral. It's like a simple Green's theorem type of problem. So we want to evaluate this integral, y cubed dx minus x cubed dy, where c is the boundary of the positively oriented annulus with inner radius 1 and outer radius 2, centered at the origin. So it's kind of like a donut. So what we're going to do is we're going to use Green's theorem specifically. I know there's like a bunch of different ways you can write Green's theorem, but I will show you what we're going to use here. So let me get the iPad out. Let's see. Alrighty. So we have this integral here. C of, I believe it's y cubed dx minus, what was it? X cubed dy. So we're going to use Green's, as I just said, which says that we can write this as a double integral. Here, let me write it properly here. Write the whole thing. So we have, if we have an integral of this form, we have p dx plus q dy. We can write that as a double integral over some d of the partial of q with respect to x minus the partial of p, oops, that's not my best handwriting there, p with respect to y, and then dx dy. So there, the p and the q are the coefficients of these dx and dy terms. So obviously we are set up for that. We can see that that's like very clearly of that form. So we can directly apply this formula here in the following way. So let's go ahead and write this as a double integral. I'm not going to write the bounds because we're going to convert to polar here in just a second, but just to kind of show what we're doing here, these derivatives are very, very obvious. So I'm obviously not going to go over those. dA, so we're going to convert to polar. And normally I would write the polar conversions here, but we're just going to use the x squared y squared one. So that's going to allow us to, oh, hi Justina. That's going to allow us to write our double integral like this. I think I got something in my eye. We'll have this negative we're going to go ahead and pull out. So we just erase that. I have the double integral. Forgot I need to write my bounds. So we're going to go 0 to 2 pi. And then our radius is going to go from 1 to 2. And we'll have 3r cubed dr d theta. And that's because we pick up an r with our dA there, and then the r squared comes from that x squared y squared. Okay, so this is going to be really easy to integrate. We're going to be able to write that is equal to negative integral from 0 to 2 pi of, let's see, it would be 3 over 4 r to the fourth from 1 to 2 d theta. And what is that? What is this going to give us when we plug that in for r? Well, that would be 3 over 4. 2 to the fourth is what, 32? 16? Got 2, 4, 8, 16. So that's times 16, and then that's going to cancel that. So this will just give us 12 here. Just like 12, and then minus when we plug in a 1 there, that will obviously just give us 3/4. And that is equal to, let's see, 12 times 4 is 48. 48 minus 3 is 45 over 4 for the evaluation of our integral there. So looks like we're out of room. Can you guys see that? Did I write over my face? I have been notorious for that. Only just a little bit. 45 over 4. Let me just rewrite this way. That's 45 over 4. And that's just what's evaluation for this. So we're going to plug that 45 into 4 back in that integral and then integrate with respect to theta, and then that'll finish this one off. So let's go to the next page. Oops, I zoomed in a lot there. Hold on. Ooh, I can do it. Come on. There we go. Actually, maybe I should zoom in a little bit. It'll give us more paper to work with. So of negative, the integral from 0 to 2 pi, I believe it was 45 over 4 d theta, right? Let's go back and check. Yes. So we can pull that 45 over 4 out and get negative 45 over 4 integral from 0 to 2 pi of d theta. And obviously that's just going to give us a theta, which is only going to contribute a 2 pi term, because if we plug in 0 for theta, we're going to get 0. So that means our final answer for the evaluation of this integral is going to be negative 45 over 4 times 2 pi. And the 2 is going to make that a 2. So we'll have negative 45 over 2 times pi. And let's see what answer choice that is. That is answer choice A. So that will be our evaluation for that integral. Let me get chat up again. Alrighty, so let's go on to the next one. I'm going to be skipping number 2 because it's the topology one I don't want to do. So I'm just going to leave it at that. And let's go on to number 3. So let me bring that up for you. Here we are. Okay, number 3. So we have x, y, and z are vector spaces of dimension 7. We have a sub 1, and a sub 2 are subspaces of x of dimension 4. We're going to define b sub I to be equal to this function f acting on those a sub i's. We're going to let f go from x to y, g go from y to z, be linear maps, such that g composed with f is not bijective. And we want, that's just the definition of a linear map in restriction. Okay, so, yeah. So we want to know which of the following cannot happen. So let me get the iPad back up here. So the thing we're going to show, basically, is one of the restrictions is that f composed with g is not bijective. That's just stated. So we're going to kind of like contradict this statement here. And we want to know which answer choice will do that. Now, I know the answer, so I'm not going to go through all 5 of these and discuss them at length. I'm just going to go over the one that is the answer. And the answer is going to be D. I believe it's D. Yes, D. Which is that G restricted to B sub 1 plus B sub 2 is surjective. So this is not possible because this implies this. But I'll show you why here in a second. So if G restricted to B1 and B2 is surjective, that means that G restricted to F of A1 plus F of A2 is surjective. And that's just by definition of B. B sub I, if you remember, is defined as the function acting on A sub I. So that's just the definition there. So I'll just do this to show that I mean is surjective. And so then we can say that this means that G composed with F restricted to A1 plus A2 is surjective. But I believe because of linearity, I believe it is because of linearity, that this surjectivity implies, I guess like in this case, surjectivity implies injectivity, which implies bijectivity. So we have that G composed with F is bijective. Also, I wrote this wrong. It's not F composed with G, it's G composed with F. Just misread from the problem there. Otherwise, we would not have completed our proof. My face is in the way that says bijectivity, but basically, in this case, one implies the other. So that means we have bijectivity if we have one. So that means we have G composed with F, which is bijective, which is a contradiction, and that gives us our answer choice, which is D. Alrighty, so let's go on to the next one. I think this one's pretty fun. Here, let me go on to the next page here and get this problem up for you guys. Alrighty. There we go. Is that too? That might be a little too far up. There we go. Let me check chat real quick. Yep. It's quite a day in chat today, but that's all right. Okay. So for number 4, we want to know for what values of a does the system y equals x cubed minus 6ax squared plus 33, and that we have y equals a have 3 solutions. Okay, so let's just go ahead and write down our equations. Let me get this window off here. We have that y is equal to x cubed minus 6ax squared plus 33, and y equals a. So basically when we have, this is a cubic, so when we have a cubic, I'll just kind of like sketch a graph to show you what we're talking about. We have a possibility for, that's not a great curve, I'll be honest. I can do better. Will it correct me? Oh no. Yeah, no, that didn't help me at all, did it? All right, we'll just have to be smooth. We have a possibility for 1, 2, and 3 solutions. One solution would be like above or below down here. 2 solutions would be if it just touches the curve down here and comes across to one other part over here. And 3 solutions would be straight through the middle of that curve in there somewhere. So we want to know the behavior of the curve to see the places, or basically the intervals, where we would intersect that 3 times. So in order to find the behavior of the curve, we are going to use a derivative test to show. So we're going to take the derivative of this with respect to x. So we're going to do dy over dx. And that is, let's see, I don't know why I'm looking at my notes because it's just a derivative. 3x squared minus, would that be 12? Yeah, 12 ax, and then that 33 is going to go away. And so we're going to find the zeros of this. So we're going to set this equal to 0. And then we're going to factor a 3x out of this. So we'll have 3x times x minus 4a is equal to 0. So we have from this, we have that x equals 0 and x equals 4a. So let me kind of sketch a graph of that behavior here. Let's get a nice graph going. I don't think that other sketch was very good. Okay, so we have at some point over here, well, I don't know if I need that. I think I just need a horizontal line here to sketch this out. So we have, for some point, let's put it up here. Let's say this is 0. Graph goes up to 0 before it changes behavior. Then it goes down here. That's, oh, it curves, so it curves there, but it didn't curve earlier. Oh well. We'll say that this is at the point 4a. This is to show like where we're at. That's not the curve. I guess I should have used a different color for the curve. Maybe I'll do that right now. See if I can't go over it. Oh dear. Oh well. And then it goes back up like that. So for, let's see, let's keep using red. So for this area we want positive, and for this area we want negative. Whew. So let's see. On the eraser right now. So f of 0 is going to be equal to 33 minus a, because y equals a, and these will all go to 0. So from that, and that's equal, that needs to be greater than 0, because we want it to be positive from over here. So that means we'll have that a is less than 33, because we got to flip that inequality once we divide by the negative. And then for f of 4a, here we're just getting the bounds for our solutions where we have 3. We're getting the bounds for the areas on our curve where we can have 3 solutions. And f of 4a, well, if we plug 4a into this, we're going to have, let's see, 4 cubed is 64. 64a cubed minus, this be 6 times, I don't know why, 6 times 16, which is 60 plus, wait, plus 36, so it's 96, right? Minus 96, somebody checking on that. A squared plus 33 minus a. So here we can use the rational root test to find some possible values for a, and we're going to check a equals 1 because I know that, oh, you can't see. You cannot see, let me just move my face. Oh dear, that's not my face. Let's just move me up here for the time being. Hello, now you can see the iPad. The curtain's been peeled back, I'm writing on the iPad. Rational root test for a equals 1. And so when we plug 1 into that, we will get 64. We want a value where this is equal to 0. So we get 64 minus 96 minus 1, and that is equal to 0. So we have our value for 1 here, but if you remember for this 4a, we want it to be negative, so we're going to have that a is, wait. Yeah, we will have that a is greater than 1. So our bounds for, I'm still blocking the problem. No, no. All right, anyway, so we'll have that a is bounded by 1 and 33 like so, and that is answer choice D there. So yeah, that's our interval of this graph, where we can have 3 solutions. So that's like, from 0 to 4a. Not from 0 to 4a, from 1 to 33. From 1 to 33, we can have 3 solutions. Okay, so let's go to the next one, and I will move my face back to where it belongs. I'm tall enough as it is. I don't need to be higher on the screen. Slide it down a little bit. There you go. You guys don't need to see that I'm writing stuff. That's too much. That's forbidden knowledge for you to know that I'm actually writing and that there's not a hidden person in here somewhere doing the math for me. Got to keep the mystery alive. Okay, so next is number 5. So let me flash that up here. So we have this system, this simultaneous system of differential equations. Now, keep in mind I haven't taken differential equations, so although I understand the math that I'm doing here, my explanation may be sort of subpar for kind of like why we're doing things, so I apologize if that is the case, but I'm doing my best for you here. So we have that x prime of t is equal to y prime of t minus x prime, minus x of t over 2, and y prime of t is equal to x of t over 4 minus y of t over 2. And we have our conditions here that we're going to use at the end, that x of 0 is 2 and y of 0 is 3. And we want to know for the question, what is the limit as t approaches infinity of x of t plus y of t? I believe this one is pretty long, but it's interesting. So let's get this out of the way here. Alrighty. So we have let's just write out our equations first. We have y prime of t is equal to, I said y prime and wrote x prime, didn't I? Is equal to y of t minus x of t over 2. And we have that y prime of t is equal to x of t over 4 and minus y of t over 2. Like that. So, and then I guess we can write, well, I won't write our initial conditions because I think I'm going to have to use multiple sheets of paper and I'm not going to use them yet. So we're going to want to write these equations as a matrix. Now we can kind of like rearrange these so that the x's and y's are lined up, so we can see how it's going to go in the matrix. So we'll have 1/2 x of t plus 1 y of t, and then we'll have 1/4 x, I don't know why I did a parenthesis there, x of t minus 1/2 y of t. So our matrix is going to be like this. I use these square brackets, I believe they're called, for matrices. It's matrices. Wait, might I write a 4th there? Oh, because it's the other vector. I got really confused for a second, sorry. So we got 1/2, 1, like that, and then that will be times xy. But yeah, as I was saying, I write these square brackets for these because I find that it is less confusing for me, so I can like really clearly state that it's a matrix. I know some people vehemently object to that, but I don't think it really matters as long as you know that we're talking about a matrix in this case. Anyway, so we can write this. This is kind of the standard way to solve these kinds of problems with a matrix, I believe. Like I said, I'm not super nuanced on the finer details. But anyway, we're going to solve, or we're going to write this as ix minus a. And our solutions are going to be linear combinations of e to the lambda sub I t, where lambda sub I are the eigenvalues of the matrix. Eigen. I'm just going to write eigen. I'm just going to write eigen. Yes. So I'm going to go ahead and skip that. Or really just kind of like write that. So we'll have x plus 1/2, -1, minus 1/4, and x plus 1/2. So from that we can get this. We'll have that x plus 1/2 squared minus 1/4 equals 0. So that'll give us x plus 1/2 squared equals 1/4. And that'll give us that x plus 1/2 is equal to plus or minus 1/2. And that means our values for x, let me make sure you're not getting cut off here. Our x is 0 and 1. So yeah, I think I can write this here if I squeeze it in. So we can write our linear combinations now. We'll have that x is equal to, we have some constant a1 here times e to the negative t. And then we're going to have plus some constant b1. And then very similarly for y, we will have times a2. What is it? E to the negative t. I think it's just the same. E to the negative t plus b2. And we're going to need to solve for these constants, and then we'll basically be done with the problem. So I will do that on the next page. Okay. Let's see. What do I have here? Yes, so we're going to plug into our original equations now. Sorry, it took me a minute. So let me go ahead and write all of our equations here at the top. So I can kind of show you what we're doing algebraically here. Y, t. Actually, let's write it in the form we had before. It's like -1/2 x of t plus y of t. Oops. We're going to use this to set up a system of equations that we're going to use to solve for our constants. So we'll have y prime of t is equal to 1/4 x of t minus 1/2 y of t. And our equations for, we also have, should I just write like and? Why not? We have that x is equal to a sub 1 e to the minus t plus b sub 1, and y is equal to a sub 2 e to the minus t plus b sub 2. Basically, we are trying to relate these constants in a way that will let us use our initial conditions to solve for them, and then once we have solved for them, we can take the limit, and that will finish our problem off. So let's go ahead and plug these into these two equations. Like plug them in this way. So that'll give us, let's see. Just trying to make sure I'm doing this right. So I keep looking at my notes. So I have -1/2, and x is equal to, I have a1 e to the minus t plus b1, and we're going to add a2 e to the minus t plus b sub 2, and that's going to be equal to, we can have 1/2 e to the minus t times a1 plus a2 And then we'll have... Oh, yeah, there's a minus 1/2 there. Okay, I should just look at the math and not my notes because it'll be faster. Negative 1/2 b1 plus b2. Is that off screen? No, we're good. Okay, so we can write it as that. Now we can construct an equation relating the coefficients here. So we have like new, just so you can understand what to do, a new equation from coefficients. We will have that a1 is equal to 1/2 a sub 1 minus a sub 2, which implies that we have a sub 2 is equal to negative 1/2 a sub 1. And on the other side for our b equation, we'll just right off the bat have that b sub 2 is equal to 1/2 b sub 1. Right? Am I skipping ahead? Did I have to plug that into the other equation to make this thing? I don't have it in my notes, but I think I do. So that would be... Is that even right? I might have to just do this over again. Hold on. Yeah, because why... Yeah, this is just not right. This is incorrect. If chat, you're yelling at me, I didn't see you, but I heard you. This is just not mathematically correct. This is a travesty is what this is, but it's a study stream. It's all good. So that's not even true. This is equal to e to the minus t times negative 1/2 a1 plus a2. And then this will be minus 1/2 b1 b2. In our second equation, we'll have 1/4 times a sub 1 plus b sub 1. I need the e to the minus t in there. So e to the minus t plus b sub 1. And then we'll have minus 1/2 times a2 e to the minus t plus b sub 2. And that will give us e to the minus t times, let's see, it would be 1/4 a1 minus 1/2 a2, and then that will be plus 1/4 b sub 1 minus 1/2 b sub 2, just in case we needed to use that second equation there. This is our second one. Let me check chat real quick, see if anybody was yelling at me. Nope. Got 5 viewers. It's a dead stream. It's okay. It doesn't seem like it's going very well for me, so it's all good. Let's see. Yeah, so now we need to do those equations relating the coefficients. So we'll have a sub 1 is equal to 1/2 a sub 1 minus a sub 2. And the other one will be negative 1/2 b sub 1 plus b sub 2. Yes. And so when we plug in our initial conditions here, we will have new equations. So let's do that. So let's plug our, just go ahead and give this an arbitrary and we'll call these two star. So it's like plug, I said plug and wrote a B, it's all right. Plug, our conditions were x of 0 is equal to 2, and y of 0 is equal to 3. I'm going to plug that into our star equations. So it's going to give us the two new equations. 2 is equal to a1 plus b1. And using our equations that we just made to relate our coefficients, we're going to have minus 1/2. Okay, that's it all on the screen. That's good. A1 plus 1/2 b1, but we're going to write that as 6 is equal to negative a1 plus b1. So now we're going to add these equations, and we're going to solve for our b's. We could solve for our a's here, but it does not matter, as when we take the limit as t goes to infinity, when we plug in that t, or when we take that limit evaluated at infinity of that e to the minus t, that a term is just going to disappear. So the only values that really matter here are our b values. So seeing that, we can save ourselves some work. So let's add these equations, because then our a's will cancel. So we'll add, and we'll get that, let's see, we get 6 plus 2, we'll get 8. The a's will cancel, and we'll get 8 equals b1 plus b2. But we know that, no, because they're both b1. I forgot we made our substitution for that. So 8 is equal to 2b1. And that means b1 is equal to 4, which means from, did I write plus there? Oh my gosh, I'm losing my mind. This is supposed to be equals. Equals. Right? There's no negative. What am I doing? My brain doesn't exist. This is a positive. I should box these so they're like distinct. Oh, geez. Because they are important. I'm going to keep these notes for later, so it's kind of late for it to be convenient for stream. But those are the equations we're using relate there. So that means that b2 is equal to 2. I think I can squeeze this in here. So when we evaluate our limit as t goes to infinity of our x and y equations of star, and they're being added, but we can see that the a's die, and what we're left with is b1 plus b2, which is 6. And 6 is answer choice B. So that's that. Hopefully that was it was possible to follow that. I don't know if it was. I don't know if it was possible to follow that, but I gave it a good shot. Anyway, hopefully some of that made sense for you. So next is the triple integral I was talking to you guys about. So we'll do that. Let's go on to the next page, and I will put it up on the screen for you. So we have B is the unit ball. X, Y, Z, and R3. It's just the definition of the unit ball there. X squared plus Y squared plus Z squared is less than 1. We want to evaluate the triple integral over that unit ball B of the function 3x squared plus Y squared plus Z squared plus 2 dx, dy, dz. So because we are dealing with a sphere, a ball, we are going to convert this into spherical coordinates. So I will write the substitutions down. Please correct me if these are incorrect, but I believe it is x is rho cosine phi sine phi. No, it's cosine theta. I already messed up. Cosine theta sine phi. we have y is equal to rho sine theta sine phi. Z is rho cos. Is it cos phi or cos theta? Cos theta feels right. I'm gonna have to look that up actually. Let me see. Spherical. Wow. Spherical coordinate substitutions. I feel like it's sine theta. Why do I think it's sine theta? Is it sine theta? Is that why? Or cosine theta, sorry. No, it's phi. It's rho sine phi. Huh. Alright. Cos phi. And then we have this fact that rho is rho squared, right? Since I already have it up, now I'm actually going to cheat. We have that, yeah, rho squared equals x squared plus y squared plus z squared. So if you recall, our function that we're integrating over is 3x squared plus y squared plus z squared, which is very close to what we want for this row thing here. Oh, plus 2. That's important. So that means we can rewrite this as 2x squared plus 2, maybe just 2 times x squared plus 1, but doesn't really matter. And then that's going to be able to be substituted as rho squared, but I'll go ahead and write it out. So that's going to be rho squared. And so with that, we can set up our triple integral. So we'll have our triple integral. Oh, I need to write what it's rho squared. What dv is. We have dv is equal to, I believe it's rho squared here. Rho squared sine phi d rho d theta d phi. Okay, so let's go ahead and write our triple integral. So we have d phi in the back, so that's going to be 0 to pi. In the middle we have d theta, so 0 to 2 pi. And in the front we have rho, which will go from 0 to 1, because it's the unit ball. So let's go ahead and make our substitutions here. So we have 2x squared, and x is that right there. So we will have in the front here 2 times rho squared sine, cos squared theta sine squared phi, right? Yes. And then that's going to be plus 2. And then that whole thing at the end will just be rho squared. So, I guess, yeah, because we have to multiply by rho. So let's do plus rho squared, and then we'll have a rho squared here, sine phi. Is this going to go off the screen? No, I think we're good. Sine phi, and then d rho d theta d phi. Okay. So let's go ahead and multiply our rows through. Since we don't have any crazy terms, we can just do this, the rows with the, what's it called? The power rule, so no issue there. So that's going to be equal to the triple integral. I'm not going to write the bounds, except for the one we're about to do, just for the sake of reducing the amount I have to write. So we're going to have 2, let me make sure that is a rho squared. I don't know, it's rubbing me the wrong way. I feel like it's not a rho squared for the dv part. It doesn't have it here. dv equals rho squared sine phi. Okay, so I was right. That was just from my brain. Thought I made that up for a second. So we got 2 rho, so that rho squared is going to make that a rho to the 4th. Let's go ahead and distribute the sine too while we're at it. So we'll have cos squared theta sine cubed phi. That's going to be plus 2 rho squared plus rho to the 4th d rho d theta d phi. Okay, So let's go ahead and apply the power rule here, and then we can evaluate. So I'm just going to write, I'm going to not write the integrals and just do the algebra for the evaluation for rho here at the bottom, and then I can rewrite our solution in the integrals on the next page. So we'll have, let's see, that'll be 2 over 5 rho to the 5th cosine squared theta sine cubed phi, plus this will be 2/3 rho to the 3rd plus 1 over 5 rho to the 5th. And that's going to be evaluated from 0 to 1. Now, every single term here has a rho, so that 0 is going to not contribute anything. So, and the 1, since it's all being multiplied, is going to contribute effectively nothing as well. So all we've done is pick up our fractions there. So we're going to get, this is equal to 2/5 cos squared theta sine cubed phi, and that's it, right? Yeah? Is that the whole integral? Am I missing something? Oh, no. That's not correct. Because these terms should have picked up from when I distributed the sine phi, they should have picked up a sine phi. So that's going to be plus, yeah, it didn't feel right. Would that be 2 sine phi plus sine? Oh, I need my coefficients, my fractions here. So that's going to be plus 2 over 3 sine phi plus 1 over 5 sine phi. And then that's going to be, well, we won't write the d theta d phi part yet. Let me check that. If there's anyone in chat, can you verify that that's correct? Verify that. Looks like we had some decent viewership earlier. We peaked at 13. That's not exceptionally high, but it's not very low either. Excuse me. So, yeah, this rho squared became a rho to the 4th and picked up a sine. Yeah, so that 1/5 is the sine there, and then 2/3 sine phi, because it was just a 2. It only picked up the rho. Yeah. Okay, I think that's correct. So let's go on the next page. So we will have the integral from 0 to pi and from 0 to 2 pi of, I don't even remember what we had. 2/5 cosine squared theta sine cubed phi plus 2/3 sine phi plus 1/5 sine phi d theta d phi. Okay. So we need to figure out how to get rid of our cosine theta there. So it's worth, so let's go ahead, note, this is a double angle formula for cosine, that 2 times cosine squared theta is equal to the cosine of 2 theta plus 1. So we're going to go ahead and make that substitution, which will make our cosine much easier to deal with. So that means we've got this double integral 0 to pi, 0 to 2 pi of 2 over 5 times, let's see, that would be cosine of 2 theta sine cubed phi plus another sine cubed phi as it multiplies through to that 1. And we're going to have plus sine phi. Oh, we need our fractions there. Keep wanting to forget those. I might have already, honestly. Wait, yeah, that matters. I need a parenthesis there for that 2/5 because it's being multiplied to both of those terms. Plus 2 over 3 sine phi plus 1 over 5. Let me just combine these fractions real quick so I don't have to keep writing 2 terms here. So what's 2/3 plus 1/5? Let's see, so we'll have This is 3/15, and that is 10/15, so we'll have 13/15, right? So 13 over 15 sine phi, d theta, d phi. Okay, so we only have one theta term now that we have to deal with. So let's go ahead and make a simple u substitution to make this integration even easier. So we're gonna let u equal 2 theta. That means that du equals 2, which means we just have to pull 1/2 out to keep this accurate. So we'll have 1/2 0 to pi. I'm not going to write the bounds of integration for this, even though it's poor math etiquette, I guess, just because we're going to substitute back in later. That'll be 2 fifths. Wait, do I get to pull the half all the way out? Yeah, I do, because it's being changed for the whole thing. Yeah, okay, I think that's correct. 2 fifths times cosine u sine cubed phi plus sine cubed phi plus 13/15 sine of phi, d theta, d phi. Okay, so integrating that, we will get be negative sine, so we get minus 1/2 integral from 0 to pi. Integral is still not going to rewrite that just yet. Put the minus already out, so we get sine. Let's go ahead and actually put in 0 to 2 pi, because this will be sine of 2 theta sine cubed phi. There's a lot of sine function in this integral right now, isn't there? Sine cubed phi plus sine cubed phi plus 13 over 15. Wait. That's not correct. No, that is correct. Yeah, sine phi, and then we pick up a theta here because we integrated. On this term, d theta, d phi. Okay, so we can write, there's another double angle formula that says we can write sine of 2 theta as, let me just look it up to make sure I get it right. I think it's just cosine times sine. Does anyone know? I know the chat's pretty dead. Are you talking about my voice? Are you, the quiet talking, is that my voice you're talking about, or are you talking about like behind me? There's no one else in my house. If there's quiet talking in the background, it's the voices. Like there's there's like somebody in my house and we need to call somebody. So hopefully it's just you, assuming you're not talking about my voice being way too quiet. I guess, can you give me some confirmation that you can hear me? Okay, I'm good. All right, just want to make sure. Okay, cool. Let me get back on task. I was going to look up this double angle formula for sine of 2 theta. I think it's just cos. Does anyone know? Sine 2 theta double angle. Oh dear, I started a video. Please don't. I just wanted to see what it was. No. Double angle identities. Here we go. Yeah, it's 2 times sine theta cos theta. I'm glad I looked that up because I would not have realized. Okay, so that's 2. So let's go ahead and write, we got 1/2. These fractions are out of control. Like, I'm thinking they're not going to be accurate at all by the time we're done with this problem. And then, should I just go ahead and evaluate? I guess. So we'll have 2 fifths, and then this will be 2 cos theta sine theta. Wait, I just realized this term needs a theta as well, because we didn't add it when we integrated. That's immensely important. So let's go ahead and fix that right now. Just get a tiny eraser in here and get rid of this parenthesis. Not hugely important. Plus 2/5 would be sine cubed theta, no, sine cubed phi times theta. And then that's going to be plus 13/15 sine phi theta. And then that's going to be from 0 to 2 pi d phi. Okay, so, oh geez, my head's in the way. This is constant problem. Anyway, let me just put me up there. Okay, so we can see that for this cosine theta sine theta part, it is going to go to 0 because the cosine of 2 pi is 1, but the sine of 2 pi is 0, and for, wait, yeah, 2 pi and 0 are the same. Why am I thinking too hard about this? Yeah, 2 pi and 0 are like the same angle. So sine is 0 at both of them, is what I'm trying to say. So it makes that whole term go to 0. So this will go to 0. And the only contributing piece from the other ones is the 2 pi. So then we can just plug in a 2 pi into these two thetas on the next page. So that means that this whole thing is 0. So let's go to the next page. So we have -1/2. Like I said, I'm going to be astounded if we didn't screw up some fractions somewhere. If we do, I'm just going to assume it was an arithmetic mistake, and if we can't find it easily, I'm just going to move on. But if you in the chat have already seen a mistake, please point it out, because even if I don't see it right now, I will go back and look at the comments after I'm finished with my evaluation, and I will find that mistake. You're probably going to be better at it as a group than I am by myself. Anyway, so we'll have 2/3 sine cubed phi times 2 pi. And that's going to be plus, what was it, like 13/15? Yeah, 13/15 sine phi times 2 pi d phi. That's d pi. D phi. Okay, so we can pull out a 2 pi here, and the 2 pi will cancel that 2 here. So we'll have negative pi times 0 to pi of 2/3 sine cubed phi plus, I feel like we need to do something with these fractions, 15 sine phi d phi. Is that correct? Let me check the chat again. Make sure. I might have forgotten to divide by half in the power reduction of cos theta. Let me go back and see what you're talking about. The power reduction of cos theta. I think I pulled the half out when I did that here. Like this half comes from that. If that's what you mean. Anyway, I think we're good on the calculus so far, right? I feel like I should just like stare at this page before and see if I made any mistakes for a second. We have so many weird terms and fractions that I find it hard to believe I didn't drop something somewhere. It's from the U sub. Oh, you're right. Well, I wouldn't have picked up a half integrating cosine of u. I would have picked up a 2 from this to this. What half are you referring to, I guess? Power reduction of cos theta. I didn't power reduce cos theta. I just did a u sub, and when you integrate cos, you get negative sine, right? No, that's when you take the derivative of cos. This should just be sine. There's no negative here. That's a fix. From line 1 to 2, there's a missing 1/2. From here to here, earlier still. Up here, 2/5 cos theta, 1/5 cos 2 theta, from there to there. Yeah, I'm using a double angle identity. I'm not power reducing the cos squared theta. So I wouldn't pick up a 2, I think, if that's what you're trying to say. I'm not trying to... Also, why would it be a 1/5? Huh. There's a stream delay, so I have to talk to you guys, like, I have to sit here. The 2/5 cos theta. So from here, 2/5 to here, you're saying that I should have a 1/5. Your identity has a 2 on the left side. Oh, I think I see what you're saying. There should be a 2 right here. Or I just wrote it. Oh, I see what you're saying. Oh, okay. This right here. Ah, you're right. Yes, thank you. I'm sorry it took that long for me to process. But yeah, no, there's a 2 here, so I need to pull out a 1/2 right here. I see what you're saying now. Yes, thank you. Thank you. Okay. Yeah, that makes sense. So then this will be a 1/4 all the way through. So I'll just fix that on the next page. I'm not going to like fix it on each one. But yeah, thank you. That's actually very helpful. So this will be 1/4, and there's no negative. So this is actually pi over 2 here, I think. Yeah, and the negative I fixed. Yeah. Okay, cool. I think we're good. Okay, now we need to figure out what we're going to do with this, with these fees, man. Here, let's try this. Okay, so we'll have pi over 2, 0 to pi. Let's try writing this as 2/3 sine squared. I'm going to write pi instead of phi like 50 times. I feel it coming. Times sine phi d phi. And then we'll replace this sine squared phi with 1 minus cosine squared phi. And that'll give us pi over 2. I'm writing way bigger on this page. I could have like done this all in one go, but it's all right. Times 2/3 minus 2/3 cos squared phi plus, dude, these fractions are actually killing me. There's gonna probably be some way to clear them later. I probably should have dealt with them by now. Sine phi d phi. And we're going to let, this is for like this step, u equal cos phi. And that means du equals negative sine phi. So we can use that fact right there to get rid of that. And then that means we can write our cos squared as a u squared, and then I think we can just finish that with a u sub. Although it's going to be ugly. I severely doubt this is going to be like the right answer. I think these fractions are there's something off, but I don't know. I have faith. All right, so we have 2/3. This is like a gnarly integral. Minus that. And since we have a negative here, we need to pull out a negative now, right? And that's going to be 2/3 u squared plus, geez, the fractions, 15 du. And that's, these bounds are wrong, because I haven't changed them. But I think that's good for the calculus, right? I wrote that pretty quick. So let's go ahead and take the antiderivative of this to finish the problem off. So that'll give us, see, I think I can write down here. It'll give us pi over 2 times 2 over 3u minus 2u cubed plus 13 over 15u, and that is equal to, let's just finish it on the next page. So we have, wait, I wonder if I haven't even tried to do this stuff before. If I can just like copy my writing like this, copy, paste, paste, please. How do I paste? Paste. Yeah. That might have been faster. And our u sub was what? Cos phi, right? So this is equal to, this is, oh, we don't have bounds yet because I didn't bother changing them. Over 2, this will be 2/3 cos, no, yes, cos phi minus 2 cos cubed phi plus 13 over 15 cos phi, and phi is from 0 to pi. Okay, so when cosine of pi is -1, so, and since this is an odd power, it'll also just be -1. So that, and then cosine of 0 is 1. So does that mean this whole thing goes to 0? I don't know, let's just plug it in. 2 over 3 times -1, get that pi over 2, negative out here, plus 2 minus 13 over 15. Oh no, it won't be because we're subtracting this whole thing. Minus 2 over 3 minus 2 plus 13 over 15. So that's going to be equal to pi over 2 times be what? -4 over 3 plus 4 minus 26 over 15. That is so ugly. That is just horrible looking. 2u cubed over 9. You might be right. Yeah, you're right. It's over 9. Thank you for catching that. That just makes this 2/9, and this 2/9, which makes this 4/9. Yes. Yeah, the bounds should be different, but I didn't bother changing them. I just substituted back in and used the original bounds. This is horrifying. This answer is just the worst I've ever seen. Anyway, so that gives us plus, I wonder if it'll like simplify to something extremely like normal. That'll give us plus for the first term. That 2 for the pi will cancel that, so we'll have plus 2 pi over 3 plus 2 pi over 9 plus, or minus, no, this one's minus and the other one's plus. Minus 2 pi over 9. This is plus 13 pi over 15. That's just the worst thing I've ever seen. I hate this. Should I just try to add them all together and like see if it works? Yeah, so 2/9, this is the same as 6/9, so this is 4/9 pi, right? And then, does anyone know what this is? Yeah, I don't think this is right at all. I I don't think this is the right answer because our answer choices are 1 pi, 2 pi, 4 pi, and pi squared. And believe me, I don't think this is coming out to be any of those. Yeah, I don't know. This is horrifying. X, we made an error somewhere. Does anyone see where? Is it worth going over? Yeah, move on. I'm with you. Anyway, that was fun. I'm curious to see what the actual answer is, though. Let me check. So I've been doing these this is my 5th stream, and I knew they had hints at the bottom, but I didn't know they had the answers there, even though it's like staring me in the face. D, 4 pi. Okay, it's 4 pi. That's what we got, right, guys? We don't make mistakes here on the Math Major channel. We got 4 pi. I think everyone should agree that that's what we got, actually. This is 4 pi, actually. That's what that is. That's what this fraction is. My sources, trust me on it. Trust me. Okay. All right. Yeah. Let's move on. I'm done thinking about this. This problem sucks. It was a slog, and we didn't even learn anything. The next problem is a sum. It's actually a fun sum. I don't know how many of you are familiar with calculus 2. I don't know how familiar each of you are with some problems, but I remember when I took calculus 2, which I believe is when you're introduced to kind of like infinite sums, I was like, this is the worst thing I've ever seen. Like, I've never seen anything worse in math in my life. I hate these. I never want to see them again. And then once I took a few classes with Michael and we did some sums, I realized that they're just really fun. And I don't know why I thought that. I mean, I guess I just had a bad teacher or a bad experience or I didn't get it. But I think sums are great now. Anyway, so we want to evaluate this infinite sum here. So let's go ahead and do that. I'm only off by pi over 15. That's not that bad. It's not bad at all. Okay, can you guys see? No, you can't. Almost started writing without you. That would have been sad. Don't want to leave you guys behind. Okay, so we have this sum here as n goes from 1 to infinity of log. I'm going to assume they mean natural log. I don't know why they wouldn't. The way I was taught in school, you use ln to mean natural log, and you write log. It's implied. Like they told me that if you see just log, you should assume it's a base 10 log, but I don't think any mathematicians use base 10 log. I don't think I've ever seen a problem. So I'm going to assume this is natural log, although it doesn't actually matter for the record, but I just thought I would start a discussion on that because why not? I am less cultured when it comes to the norms for math stuff than I could be. Okay, so we're going to write this. We're going to write this 1 as n squared plus 9n over n squared plus 9n. And that's going to give us, I'm just going to ignore writing the stuff for the sum for the sake of time, because after that problem, I just want to speed through these. We're going to have 9 squared plus, n squared plus 9n plus 8 over n squared plus 9n, and this top is going to factor as n plus 1, n plus 8, so that's going to be equal to, and the sum as n, watch each sum I do is going to get worse, n plus 1 times n plus 8 over, there's a log here, and there, I wrote it on that one, of n squared plus 9n. Okay, so we want to write this as a telescoping sum. I guess we could just write this bottom part as n times n plus 9. That might make it easier. Oh, it's definitely going to be better. Okay. So yeah, that means we can write this as the sum of the natural log of, what would this be, n plus 1 minus the natural log of n. This is just log rule stuff. Plus the natural log of n plus 8 minus the natural log of n plus 9. So we're going to want to write this as a telescoping sum and see if we have cancellation. I'm not going to go out like a billion terms if I need like 6 substitutions to go through, but let's just do a few of them just to see what we get. So for n equals 1, we will have the natural log of 2 minus the natural log of 1 plus, oh, and this is just 0, plus the natural log of 9 minus the natural log of 10. For n equals 2, I'm going through these really fast. If I mess this up, forgive me. Natural log of 3 minus the natural log of 2, so we already have our like first cancellation there, plus the natural log of 10, so that cancels that right there. This is already looking good, minus the natural log of, what's n, be 11. Could you also take the log outside and have a sum convert to a product, or am I missing the order of it? Confusing the order of it. Take the log outside and have the sum convert to a product. I'm not sure. I think writing it as a telescoping sum here is the easiest to show convergence, because I can already pretty much see the pattern. Like this, here, let's actually use colors to show. So like this is going to cancel this, which is going to cancel this, and same thing here. This is going to cancel that, and that, and that, and that. And our last, our answer is going to be this natural log of 9. So yeah, let's verify that. So we have, let's do n equals 3 and just make sure that that's how it's going to go. So that we'll have the natural log of, let me erase these lines, but you get the picture. Yeah, so this is going to be the natural log of 4 minus the natural log of 3. Yeah, so that cancels like I was saying. And then this is going to be plus the natural log of 11, which cancels that. Yeah, this is just how it's going to go. Times minus the natural log of 12. And they're just going to alternate canceling, which means our answer is the natural log of 9 is what it converges to. Because we have this telescoping sum cancel all the way down. Okay, so that is answer choice E. We have an answer choice, ladies and gentlemen. Ignore the last problem. We did it perfectly, flawlessly. I've never made a mistake in my life. That's my official stance, is that I've never actually made a mathematical error. It's impossible to disprove. Okay, for this next one, I don't fully, like, I understand it, but I think I'm missing something extremely simple. So let me walk you through here. So we have this algorithm where we define C and B as 2, and we have our input A, and we run this program. So like, let me run you through it. So it's basically like, while B is less than or equal to A, if A% B, that's basically like mod. Like you're taking a modulo operator there. So it's like if you take A mod B, which in this case would be 2, to start, if the remainder is equal to 0, you set C equal to B and A equal to A divided by B. Otherwise, you just, what's it called when you add 1? Iterate. You iterate B. So basically what you're doing is you're factoring this, is what this is doing. It's finding the factors. So the prime factors and increasing weight or whatever. So for our first loop, we'll have C. Well, let's get the factorization of this number. I'm just going to look it up because I don't actually know what it is. What is it? 3. You can't see what I'm writing, but it's fine. It's 368,039. Let's get the factors of that from Wolfram Alpha instead of going through trying to figure it out on our own, because we're incredibly smart people. I did a video on divisibility rules. I know how to Let's see, what's the command in Wolfram? Is it like factors? Okay, yeah, so that's pretty simple. We've got this is equal to 7 cubed times 29 times 37. Yeah, I didn't know that off the top of my head. Anyway, so for our first loop then, c is equal to 1 to start. So b will be iterated until b is equal to 7, because that's our first factor. So we'll have b equals 7, and our input is, our a is this. So we'll have that a mod b is equal to 0. So that at the end of the program, we'll set c equal to 7, and our new a is going to be equal to 525.77. For the next loop, we'll have b is equal to 29, because that's the next factor. And c is equal to 7 from the previous. So this is like the first, this is the second loop. C is equal to 7. Then at the end, we'll have that c is equal to 29. And when you divide 29 out of this, you'll have that a is equal to 1813. And the third loop is we'll have b equals 37, because that's the last one. And c is equal to 29. And then we'll have c is set to 37. And a is equal to 49. So here's my question for you guys. From the way I see the program is written, I think that this should run again until b is equal to 49. And then our c output should be 49. Because I don't see why it would stop here. The hint or whatever says that it just outputs the largest prime factor. So the answer is 37, which I can see like it would go through 37. But can anyone explain to me, am I missing something basic as to why it wouldn't run the next loop? Yeah, so does anyone know why it doesn't run again? I don't know. The answer is D. Like, according to whoever wrote this, the answer is D. And 37. Like, it stops here. But why does it stop here? I don't see why it would stop here. Unless I just, like, missed some finer detail here. Does anyone know? I gave some time for it to go through. Can I show the question? Yeah, sure. Oh, yeah, I guess that would be important now. Since I'm asking you about the question, right? Here. There we go. So this is the algorithm. I've taken a computer science class. I know, I've programmed. It's been a while. I took a C++ class and did some MATLAB and stuff, but it was pretty intensive. But I'm not by any means the computer guru. I'm still very much a novice, so I don't know if I'm just missing some like order of operation here or why. But I don't see why, given what I've written, that it wouldn't run again for when a is equal to 49. If I'm just missing something. I don't know. 37 is definitely the answer because it's not 7,511. I don't even know what that is, or what significance it has for the problem. It will keep going, but C won't change. Well, if B is what's it called? Iterated until it's equal to 49, the while loop will still be true because B is less than or equal to A. And then because B is 49 and A is 49, A mod B will be 0. So I don't see why it wouldn't set C equal to B for that last one. That's what I'm trying to say. Yeah, you're fine. I'm sorry about that not showing you the program. But it's a pretty straightforward loop. It's not super difficult, but yeah, I don't know. I really don't know why it doesn't run again. Maybe I'm wrong. Maybe they're wrong. I don't know. I don't want to say they're wrong because I don't know who wrote this. I don't know who I'll be claiming is wrong, but I don't see why I wouldn't run again to 49. But anyway, 37 is the answer provided. Let's go on to number 9. So we say f from r to r, a function from the reals to the reals, is lower semi-continuous, provided that the preimage on the interval a to infinity is open for every a in r. And we want to verify which of or how many of these statements are true. I'm going to kind of like blast through these 3 proofs, I guess, pretty quickly. But the answer is that they're all true. So let me kind of sketch out why in lieu of a more thorough proof. So this, the characteristic function on, on -1 to 1, the way that works is it outputs 1 if x is on the interval, and it outputs 0 if x is not on the interval. So it's basically just like seeing if x is in the set or in the interval. So if I'm just going to do this with 3 cases. If a, keep in mind we're trying to show it's lower semi-continuous, so we're trying to show that want to show preimage of a infinity is open for all a in R. So basically we want to show that no matter what our a is, we have an open open preimage. So if a is if a is less than 0, then this preimage is of -1, 1 is the whole real line. And reminder that the real line is open and closed, but it is open, so we're good. If a is, let's see, if a is between 0 and 1, then this, what's this thing called? The characteristic function. Yeah, the characteristic function, or the preimage of the characteristic function on this interval is equal to -1, 1, if and only if one is on a infinity and the characteristic function, or the preimage on 1, 1, of a infinity equals this. I'm just an x. It's just the singleton 1, which is equal to this interval here. So there's your quick sketch for that. To not explain it, but write it. And then if a is greater than 1, we'll have that it's the empty set. Because 0 and 1 are not on a infinity, but the empty set is also open and closed. Just to run through that extremely fast. Okay, so the next one is number 10. It's my brother's birthday today, and I'm supposed to meet him for dinner soon, and I have to drive pretty far, so I'm going to skedaddle pretty quickly. So, unfortunately, and number 11 takes a while, but I love number 11. I think it's my favorite problem in the set, so I'll do that one. Oops, just made myself disappear. Okay, so which of the following sets has the largest cardinality? Now, once again, I'm going to kind of sketch through this. This one is Some of these are harder to see, some of them are easier to see. The answer to this question is A, that a set of topologies on the real line. It is like many magnitudes of higher cardinality, but I will kind of like sketch out a proof as to why the other four options are bounded by 2 to the r, and then do like a really, really brief, unproven statement for the topologies, just to like show how much larger it is, but not really go into exactly why, because it probably take a while. Okay. So let's start with answer choice B, which is the set of functions in general on the real line. So this is like a pretty standard thing. So we have the set of f from R to R. If you've taken an advanced set theory class, that set of functions has a cardinality like that. I don't know if that's the right way to write it, is equal to 2 to the r. That's just like a definition for that. So that's B. That's the cardinality for that one. C is the set of functions from Rn to Rn. And to get this one, you're going to have to note that the cardinality of Rn is equal to the cardinality of R, which is the cardinality of the continuum C, or in my case, whatever that is, whatever I just drew. So by that, we know that this one, cardinality of this one is less than or equal to 2 to the r, because this function this is the set of continuous functions. I didn't write that. It's worth noting. Continuous. So the set of continuous functions, given this fact that I didn't even write that correctly. It doesn't make any sense. Anyway, yeah, these set of those functions that are continuous because of this note here are going to be less than or equal to in cardinality to answer choice B. So answer choice D. I don't even remember how to do this one, so let me check real quick. Okay, yeah, so you have to use this fact. Use the cross product. So the functions from Z to R are less than or equal to, I should have cardinality there. There we go. Are less than or equal to in cardinality. How am I supposed to say that? Dude, my brain is not functioning today. Less than or equal to? Less than or and equal? I don't even know. My brain is not functioning. It's less than or equal to Z cross R, which is equal in cardinality to the continuum, which is equal to fancy C. So we can apply that here. This answer choice says, I didn't write it out. This one is functions. This is for D. What it is. Functions from Z to R to the cardinality of the continuum. Yeah. That's what D is. So anyway, so we're going to use that fact there. So applying it here, we have thus, thusly we have Z to R to the cardinality of R is less than or equal to in continuity to Z cross the power set of R. And that is equal in cardinality to the power set of R, which is defined to be 2 to the R. So that is the same as this one there. And E is the set of all subsets of planes that pass through the origin of R7. So like set of subsets of planes through origin of R7. Yeah, so this is going to be less than or equal to in cardinality to the power set of R7, and the power set of R7 is equal in continuity to the power set of R by facts I've already written for you, which is equal to 2 to the R. And good, I didn't actually cut off. I stopped right at the right time. Okay, and then so for A, let me just write out, for the answer choice, let me just kind of give a brief explanation for why the topologies are so much larger. So for A, for some, for K, which is an arbitrary, I guess, let K is a better way to write that. Let K be an arbitrary, is that how you spell arbitrary? Arbitrary, sure, I'm not an English major. Arbitrary size, infinite size, sorry, that's important. For some set X, a topology on X is a set of subsets of X of X, is that off? No. And we know that X, because of its infinite size, X has 2 to the K subsets. Wow, my handwriting is just terrible. 2 to the K subsets. And there are 2 to the 2 to the K collections of subsets of X. When we have that X is equal to R, we get 2 to the 2 to the 2 to the R topologies. So that's a lot more. Exponentially more, in fact. So that is why they're not equal. Let me see. Yeah, my brain's fuzzy at the moment. So my apologies. Anyway, so that's probably not a fully correct or technically accurate way to write that, but that's kind of to give you the order of magnitude of difference between the topologies in the real line and the other things that we just discussed. Okay, so let's go into number 11. Number 11 is a fun, complex problem that took me longer to figure out because I kept messing up the arithmetic and stuff than it did because of the difficulty of it. But let me show you number 11. This is, like I said, probably my favorite problem here. So we have let z equal x plus iy for x and y on the real line, and consider, or x and y are real, and consider a function f of z is equal to g of xy plus I of h, or I times h of xy, with g and h being functions that go from R2 to R. Suppose f is holomorphic and g of xy is equal to x to the 5th minus 10x cubed y squared plus 5xy to the 4th, and we have this condition that f of 0 is equal to I. We want to find what f of 1 plus 2I is. Okay, so the important facts here are, well, really the only important fact that we're going to use here, except for our initial condition, is that f is Sorry, holomorphic. So that means we can use Cauchy-Riemann equations to hopefully find a way to solve for... Oh, camera just died. Did my tripod die? Oh dear. Is it good? Is it good now? I can't tell. I think it's good. Yeah? Camera good? Why did you die, sir? There we go. Okay. Now it's actually good. I think it's because I put my notebook over near it and I might have like bumped it a little and then it just started crying. I've destroyed it. Okay. So we have... So let's, all right, we're going to use our Cauchy-Riemann equations, which are that partial of u with respect to x is equal to the partial of v with respect to y, and the partial of v with respect to x is equal to negative the partial of u with respect to y, where u is the real stuff and v is imaginary stuff. So if you remember, our z is our function, no, not z, f of z is our function, it's which is equal to g of xy plus I times h of xy, and we have a definition for g of xy, but we do not have one for I of h. I times h of xy. So what we're going to be doing is finding our function h of xy using our Cauchy-Riemann equations. So f of z is equal to, we have x to the fifth minus 10x cubed y squared plus 5xy to the fourth plus I times h of xy. And in our problem statement, we have that x and y are real, so we don't have to worry about like getting imaginary terms out of our g of xy. G of xy is a purely real valued function. Okay, so by this we have, let's set up some equations basically. So the real part will be this, or rather g is a completely real valued function, and h is a real valued function, but it's being multiplied by I, so it's going to be complex or imaginary. So let's take our derivative of the real stuff. So we'll have du dx, and that's going to be equal to 5x to the fourth minus 30x squared y squared plus 5y to the fourth. And that is going to be equal to h prime with respect to y of xy. So to get our first equation for our first definition for, h of xy, we're going to integrate this side with respect to y. So that will give us 5x to the fourth y minus, let's see, if we're integrating, then it'll be 10x squared y cubed, and then this will be just plus y to the fifth. And then we're going to have a constant there, plus we'll just call it c1, and that's going to be equal to h of xy. And then our second Cauchy-Riemann equation is going to be, we're going to have d v dx is equal to, that's just going to be the derivative with respect to x of h of xy, and that's going to be equal to negative the derivative of g of x with respect to y. So with respect to y, that x to the fifth is going to go to 0, and we'll have minus 20x cubed y, x cubed y plus, we have 5xy there, so that's going to be 20xy to the third. And we can use this negative to go ahead and flip those signs so we don't get confused. And now we're going to want to integrate with respect to x. So we'll have our second equation for h of xy. We'll have h of xy is equal to, let's see, we're integrating with respect to x, so we're going to divide the first term by 4, so we'll have 5x to the fourth y. And we'll divide the second term by 2, so we'll have minus 10 x squared y. And then we'll have another constant plus c2. So we're going to write these two equations here equal to each other, and then use our initial condition to solve for our constant, and then we'll have a value for h of x, y, and then we can easily plug in our f of 1 plus 2i to finish the problem off. So let's go ahead and do that on the next page. Let's see if we can't do this. Well, let me get rid of these lines since I'm going to copy. I'm going to see if I can't copy it over. I feel like this is faster. Copy. Paste. That's going to be equal to. We're trying out new stream tricks today. Copy. By the way, I said this at the beginning of the stream, but I know a lot of you weren't like there for the beginning of the stream. Have there been alerts going? I tried to set up alerts, but I don't think they're working. I don't think they're working at all. Or maybe just no one. Did I just stop streaming? I think I almost hit the stop streaming button. Are we still live? Okay. That was almost bad. Okay. My finger slipped and I had it on OBS and it almost just clicked right on through there. Anyway, so we have this equation here. So let's go ahead and notice some things about this equation. That being that I dropped my power of y here. It's the first thing I've noticed. These are going to cancel. And we'll be left with 5x to the 4th y plus y to the 5th minus 5x to the 4th y plus, we're just going to call that c, and that's going to be equal to 0. Yes. So let me check my notes real quick to make sure I didn't mess up any arithmetic on the way here. Yes. Or no? That's the question. Wait. Hold on. Did I do this right? I feel like I made a mistake here. From here to here. Hold on. Does anyone see my arithmetic mistake here? I think I made a mistake on this term. Simple one. Yeah. Oh, that was from earlier. Yeah, I noticed that. No, I think I made a mistake with the exponent here. So, yeah, the derivative with respect to x is definitely negative 30. When we integrate with respect to y, we divide by 3. That looks right. No, I think that is right. Yeah, that's right. Do I have a mistake? Am I overthinking this? Let me check chat one more time. Yeah, I don't see it either. Okay. Maybe I made a few mistakes in my notes, so it's possible that's wrong. Anyway, so we have that f of 0 is equal to I, which means that we need to get an I out of this. And if you remember, do I remember? I don't. Okay, no, I'm looking at the wrong solution. That's the problem. I did this wrong and did it again, and I'm looking at the wrong part. Okay, yes. This is correct. Yeah. Dude, this is tripping me up. I'm sorry for taking so long. Like I said, my brain's about fried at this point. Looking at my own math. And I don't know what it says. What in the world? Can't we just cancel 5x to the fourth y with what? No, I'm trying to see. So in my notes, let me just talk through it and then see. By this condition, I had that c has to equal -1, but that's because what? Because if c is equal to -1, then we don't get that, right? We get that. I'm missing something else. We want g of xy plus I times h of xy to be equal to I when we plug in 0 for f, which would be when we plug in 0 for x and y. So, but why? Why is that the case? I don't know. I'm just going to proceed. I don't have enough brain power to think through this one. I'm going to trust my notes on this one. If someone in the comments later wants to point out what I'm missing. But anyway, so we want to find out what f of, maybe I'll see it once I actually do the calculation. We want to find out what this is. So if you recall our function f of z, so this is going to be equal to, so this is going to be x equals 1, and this is y equals 2, because z is x plus iy. So this means for our function, we'll have 1 to the 5th minus 10 10 times 1 to the 3rd times y squared, and y is 2, so that's going to be times 4. Plus 5 times 1 times 2 to the 4th, and 2 to the 4th is 8, 16. And that's going to be plus I times our function for h. So that's going to be 5 times 1 to the 4th plus 2 to the 5th minus 5 times 1 times 2 minus 1. Like that. So this is 1 minus 40 plus what? What is this? 80? So we'll get, what, 39? Doesn't sound right. Oh, because it's not right. It's 41. It's a positive one. Yeah. 41 plus I times, this will be 5. This is going to be 32, right? Be 37. Minus $10 minus 1. That doesn't sound right. That's 26. 5 to the 4th. Oh, it's because I forgot a 2 in here. That's because it's just not right. because there is, from here, there's a 2. So this is times 2, so this is 10 plus 32, which is 42. 42 minus 10 minus 1. Is that it? This is from the y, so that's right. This is x to the 4th, which is right, y minus 1. We got 10. Wait, I think I might know my mistake. Did I apply the... No, I'm missing a negative somewhere is the problem. That's what I'm trying to figure out. Because in my notes, I have that this is a minus. But I don't know why. Why it's a minus. So let me look very carefully through and compare what I have here. Well, for one, it says I don't have a y term here. So let's go back and see where I picked that out. That would be from here. That 20 is from... What in the world? Dude, my mind is blown right now. Hold on. I'm just going to go back really quickly and copy straight from my notes. Let's see. Fix the mistake. So I'm going to write very quickly so that I don't waste your time. Sometimes you just got to do the problem again, guys. This will be done plenty of times. I times h, times h of xy. And we already have our Cauchy-Riemann equations there. So we have du over dx is equal to 5x to the 4th minus 30x squared y squared plus 5y to the 4th, because that x goes away. And that's going to be equal to h prime with respect to y of xy, which means that h of xy is equal to 5x to the 4th y minus 10x squared y squared plus y to the 5th plus c1. And then we have minus du over dy is equal to 0 minus 20x cubed y plus 20x y cubed, which is equal to that right there, h prime with respect to x, which means our second equation for h of xy is going to be equal to 5x to the 4th y minus 10 squared y cubed plus c2. Yes. And that means that we can combine them on the next page. We'll have that 5x to the 4th y is equal, or not equal, minus 10x squared y cubed plus y to the 5th is equal to 5x to the 4th minus 10x squared y cubed plus c, and then these are going to cancel, so we'll have 5x to the 4th y minus 5x to the 4th plus y to the 4th plus c equals 0. And then we have that c is equal to -1. So f of 1 plus 2i, which implies that x equals 1, y equals 2. The real part I already calculated. That's going to be 41 because that's not changed from the problem statement. It's going to be 41 minus I times, let's see, 5 times 1 to the 4th times 2 minus 5 times 1 to the 4th plus 2 to the 5th plus, no, minus 1. Minus 1. And that's going to be 10 minus 5 plus 32 minus 1. So we'll get for our final answer 41 minus I times 37. So that's what I have in my notes. But the wait a minute. Is it this negative? Is that why it's minus I? Because we calculated the whole thing as negative h of x, and then we just put the negative in there? Is that why? I don't understand my own notes, dude. Anyway, I'm too tired to properly process this. But I have presented a solution, which is my job. So that would be A. I understood this at one point, believe it, just not right now. I'm probably going to go take a nap because I kind of feel crappy. But that will complete today's stream. Thanks for stopping by. Sorry if I was less clear today than I have been on other days, but I will do better next time. I will see if I can get those alerts working, if they don't already. And hopefully it'll look good. It'll look better next time. So thanks for watching, and I'll see you guys.